The Boeing 787 Dreamliner has now delivered over 1,276 aircraft to airlines across 6 continents. The program, which once threatened to bankrupt Boeing, as development costs alone surpassed $30 billion. The aircraft is constructed more than half from carbon fiber composite. The wings flex more than 3 meters during normal cruise. Here's what makes the Boeing 787 an absolute outlier in commercial aviation. The era of building larger and larger airliners has ended. The 850-passenger Airbus A380 has stopped production. The 660-passenger Boeing 747 left the assembly line in 2023. Both were outcompeted by a new generation of mid-size wide-bodies that opened more direct long-haul routes than ever before. The aircraft at the center of that shift is the Boeing 787. Boeing placed a $30 billion bet on a radical aircraft architecture. The decision paid off. The Boeing 787 rewrote how the airline industry operates and resets the rules for how future aircraft would be designed and built. The most important number on the Boeing 787 is 55. By weight, 55% of the airframe is built from composite materials, primarily carbon fiber reinforced plastic. The Boeing 787 was the first commercial airliner manufactured primarily from carbon composite. The only wide-body in the same structural category is the Airbus A350 XWB, which entered service 4 years later in 2015. Carbon fiber is roughly 5 times stronger than steel and 1/5 of its weight. The individual fibers are thinner than a human hair and extremely flexible on their own. Bound together with a plastic resin, they create a material that can be shaped into nearly any curve while retaining massive tensile strength. Boeing solved the manufacturing scale problem with automated tape laying. The Boeing 787 fuselage is built by wrapping carbon fiber tape impregnated with plastic resin around a rotating fuselage mold. The machine precisely controls overlap and fiber orientation to maximize resistance against pressurization and bending loads. The completed barrel is then cured inside a custom-built oven the size of a wide-body fuselage. The required upfront investment is enormous. The result eliminates an entire category of joints and fasteners. The previous generation of wide bodies required around 1,500 aluminum sheets and between 40,000 and 50,000 fasteners to form a single fuselage section. On the Boeing 787, that same section is one continuous piece of carbon fiber. The structural simplification reduces weight directly and reduces parasitic drag because the exterior surface no longer carries thousands of small bumps and ridges. The strength of the composite fuselage allowed Boeing to raise cabin pressure. Previous generation airliners typically pressurize to an equivalent altitude of 8,000 feet. The Boeing 787 pressurizes to 6,000 feet. That figure represents a 25% reduction in equivalent altitude and approximately 7.3% higher internal air pressure. Cabin humidity is also significantly higher. Both changes measurably reduce passenger fatigue and dehydration on long flights. The same structural strength produced the largest passenger windows on any wide-body aircraft. Holes that size in an aluminum fuselage would create stress concentrations at the window boundaries. Across repeated pressurization cycles, those concentrations would grow into cracks. The composite fuselage is largely immune to that fatigue mechanism. The Boeing 787 windows are electronically dimmable rather than fitted with physical shades. The wings on the Boeing 787 reflect the same materials philosophy. The wing spar is built from carbon fiber composite. The connecting ribs are machined from aluminum plate. Carbon fiber composites can elastically deform up to roughly 1.9% before permanent damage occurs. Aircraft aluminum begins permanently deforming at less than 1%. The composite spar allows the wing to bend much further without damage. During normal flight, the wingtip of a Boeing 787 moves upward by approximately 3 meters. FAA certification requires every commercial aircraft to withstand 150% of maximum expected flight load for 3 seconds. During that certification test, the Boeing 787 wing bent upward by 7.6 meters without failure. The ability to tolerate greater bending allowed Boeing engineers to design a wing with a much higher aspect ratio. A traditional wide-body wing carries an aspect ratio of approximately 9. The Boeing 787 wing carries an aspect ratio of 11. The longer, narrower wing reduces vortex drag by spreading the high pressure to low pressure transition across a longer span at the tip. Higher aspect ratio wings are the same configuration used on gliders, which carry ratios above 30 for maximum aerodynamic efficiency. The wing also uses a supercritical aerofoil. The leading edge is blunter than older designs. The upper surface is flatter. The lower surface carries a concave cusp toward the trailing edge. The configuration delays the formation of shock waves as air accelerates over the wing, raising the critical Mach number at which wave drag becomes a serious efficiency penalty. The supercritical aerofoil was first tested by NASA on a modified TF-8A Crusader. The wing fibers were laid in a specific pattern to tailor stiffness across different sections. The wing's actual shape changes during flight as aerodynamic loads vary. This technique is called aeroelastic tailoring and represents one of the most advanced applications of composite engineering in commercial aviation today. The aircraft also incorporates hybrid laminar flow control on the horizontal and vertical tail surfaces. The technology draws boundary layer air through tiny surface perforations into an internal plumbing system connected to a turbopump. Reducing turbulent flow over those surfaces reduces drag. The implementation details remain commercially sensitive. Boeing has stated that this technology can reduce fuel burn by up to 30% on the surfaces where it is applied. The composite construction created an unexpected problem. Carbon fiber in direct contact with aluminum triggers rapid galvanic corrosion when an electrolyte, such as salt water, is present. The aluminum effectively becomes the anode and dissolves. To prevent the reaction, Boeing replaced aluminum throughout the airframe with titanium, which sits much closer to carbon in the galvanic series. Titanium makes up roughly 15% of the Boeing 787 structure, far higher than on any previous Boeing aircraft. Titanium is expensive. Initial production costs exceeded sales prices, with deferred development costs projected to reach $25 billion before program break-even. The corresponding figure for the 777 program was $3.7 billion. Boeing partnered with Norsk Titanium to use wire-based metallic 3D printing for selected titanium structural parts. The process reduces total titanium consumption by 25 to 50% and operates 50 to 100 times faster than conventional powdered laser sintering. The components produced through that process became the first FAA-certified 3D printed structural parts ever installed on a commercial aircraft. The composite construction also created a lightning vulnerability. Carbon fibers conduct electricity well. The plastic resin binding them does not. Without modification, a lightning strike could fail to find a continuous conductive surface and could enter a fuel tank. Early Boeing 787 wings used thin copper strips and insulating fastener caps to route currents safely. A Boeing 787 struck by lightning departing Heathrow was found on arrival in India to have 42 to 46 holes in the fuselage from resistive heating. The aircraft was repaired and returned to service. The Boeing 787 also runs a nitrogen inerting system that fills the fuel tanks with non-combustible gas. The aircraft is the first commercial airliner to eliminate the bleed air system entirely. Wing de-icing is handled by electric heating blankets bonded directly to the slats. The electric system is approximately twice as efficient as bleed air extraction and eliminates the drag created by the bleed air exhaust ports on the underside of older wings. As of June 2026, Boeing has delivered over 1,276 Dreamliners across the Boeing 787-8, Boeing 787-9, and Boeing 780-710 variants. Production has stabilized after years of quality refinements at the South Carolina facility. Ethiopian Airlines and Biman Bangladesh placed fresh Dreamliner orders during April 2026.